Hello and welcome to us. Terrible Lizards, that's what we're doing. We are a podcast about dinosaurs. I am Izzy Lawrence, who knows very little about dinosaurs, but fortunately, over on this side of me, we have Dr. Dave Hone from Queen Mary University. We're doing this live today because Dave has a paper out today, kind of by surprise.
Well, not entirely by surprise, but yeah, we put the press release out a week ago because we were told it was coming out today, only for the journal to pull a last-minute problem, which got resolved about 4 hours ago, which is why we hadn't arranged this live one until about 2 hours ago. So yes, it wasn't a surprise. It was a surprise it came out on time.
Excellent. Well, thank you very much. If you are joining us, do say hello in things, because we will be able to see that come up. So if you want to say hey, please do. But I suppose we should really just, talk about the paper. So what is the paper about, Dave? Even though I've sort of said it in the title above us, but shh.
Yes, so it's more than a bit of a giveaway. And indeed, at least some people watching this will know what it's about because, so Jordan Mallon, who is my co-author, in fact, he's the lead author on this paper. He's at the Canadian Museum of Nature. Jordan and I had a couple of abstracts and conferences about this work a couple of years ago. The media spotted that and ran versions of the story back then. So word is kind of already been out for like 18 months, 2 years at this point, but now the paper is actually out, and that paper is basically trying to get a handle on just how big animals in general, but of course fossil animals in general, using T.Rex as our model organism for various reasons, could get, because we do have giant specimens of T.Rex, Sue and Scotty, the famous ones, both in the ballpark of 12 meters long, 7-8 tons, commonly stated figures for them. And they're absolutely massive. But we've got 30, 40 good specimens of T-Rex where you could get a handle on just how big they are. I wouldn't go outside and grab the first 40 people off the street, and the tallest one of them is the tallest human, and that's how tall humans get. It's probably not even representative of the local population, let alone humanity as a whole. That would be a very bad way of judging how big things are. But that's what we do with fossils all the time. And on one level, of course, we kind of have to. If you've only got one specimen of something and you're pretty sure it's an adult, that is your single data point. But at the same time, this is what we keep doing. And in particular, this paper is kind of deliberately a challenge to the who is biggest argument. Because if, as we think we demonstrate, Sue and Scotty aren't even that close to the kind of sizes these animals could achieve, and that's from a relatively good data set where we've got a relatively good handle on what they look like, then when we have half a skeleton of Spinosaurus, well, a tenth of a skeleton of Spinosaurus 100 years ago, which has been bombed, or some bits of Giganotosaurus which have never really been described properly, is that a big one? Is that a small one? Is that a perfectly average one? We don't even know. And therefore, kind of going, oh, who's bigger, who's smaller, it's basically bordering on meaningless. The interesting thing is the fact that they are big, not who's biggest.
Okay, so, and you picked T-Rex, from what I understand, because they are the coolest dinosaur, is that right?
Not entirely. So what we needed was an animal for which was large. So we do have some pretty good data sets. Either in theory, we could go and get them, or in practice, they are already recorded. For various small dinosaurs, so things like Protoceratops that I've done before, Psittacosaurus, Coelophysis, there are a bunch of these out there, but they're relatively small. And if you're exploring large sizes, you do kind of want to pick something relatively big. So that narrows it down massively. And then on top of that, a lot of the still relatively large ones, either the data is more or less unusable. Actually, that's pretty much it. The data is more or less unusable. So you have things like Centrosaurus, which probably weighed a few tons, certainly a couple from Alberta. We talked about them before. Extensive beds, estimates of tens of thousands of individuals, but all the stuff is basically broken up. It's all dispersed. You've got isolated skeletons. So although there are some good metrics you can get from things like femoral dimensions, we don't really have whole skeletons that we could compare. And even for the ones we do have, I don't think there's any catalogue of them, and actually it'd be a surprising amount of work to go and get it. whereas T-Rex, because it is big and very interesting to people, they've all been measured very, very extensively. And so that's a massive head start on trying to work through this thing. The second part is we also wanted to factor in a bunch of stuff like growth rate. That has been very few animals indeed. T-Rex is one of them. And so it is an animal which, yes, it looks like we deliberately picked the most hyper charismatic, but actually what we did is we picked pretty much the only one for which we had the data set that we wanted, and we had some work that had been done on the growth rate, and we had some work that had been done on potential fossil biases, and that was pretty much just it. At one point we went through a vast number of other species, and then it always just came back to T-Rex. So here we are.
It is the coolest. It's the one that most people want to work on, and therefore it has the most data.
Yeah,
it's good samples.
It's as a result of this, early press coverage from a couple of years ago with all the misrepresentation which inevitably went into that. I've literally seen on the internet someone saying we only published that paper because we were too butthurt that Spinosaurus was now bigger, and we wanted to make sure T-Rex was biggest again because we're T-Rex stans. And it's like, okay, A, that's really, really, really not true. And B, the whole point of the paper really is that you can apply this to anything. Because other than, all right, we've got things like mammoths where we've got potentially, again, dozens or hundreds of specimens. We've got a very good idea of their growth. Mammals have determinate growth and probably more constraints on their sizes. We probably have a pretty good idea of just how big mammoths realistically got. And if we want to do an extrapolation like this, it would be rather easier. But this point, again, it's not T-Rex is 70% bigger, which is the headline. It's our model thinks that T-Rex could get 70% bigger. But this is probably true of Brachiosaurus and Camarasaurus and Coelophysis and Triceratops and virtually any other dinosaur you could name. Not the 70% number, but the idea that we have found a really, really big one is almost certainly not true for anything.
70% sounds like a massive amount to somebody like me, because I think 70% bigger of me, I'm like 180 something centimeters. So if I were all 6 foot, so I'm 6 foot, 70% extra of me sounds like somebody who would be like nearly over 10 feet. That's what it sounds like.
Yeah.
But that's not the case, is it?
No, because we've got the difference between linear measurements and volumetric measurements or mass. So, yeah, as I say, Scotty and Sue. And Sooty probably, yeah.
And Sweep.
Regularly come in at like 12-ish meters and 7 to 8 tons, depending on your estimate. We are basically getting 15 meters in length, but also 15 tons. I think I just said 70%, but I probably should have said less than that. But anyway, so here's a artwork that Mark Whitten did for us. Mark got, so just to plug Mark, Mark's got a book coming on T-Rex. When he first heard that we were doing this stuff from the abstract that was out there, he said, well, can I draw this? Because I want to put it in my book. You can be a consultant and give me the advice so I get it right, and then you can use the artwork in your paper. So we did, but obviously thank you massively to Mark. So yeah, in the foreground is, I think it's Scotty actually rather than Sue, but it doesn't matter. They're comparable in size. So in the foreground is what we're used to thinking of as a really big T-Rex, the biggest T-Rex we have found. And the one in the background is our hypothetical is probably the right word, but I'd say our hypothesis, our estimate size of a very large T-Rex. And yeah, it's not that much longer, but it's massively, massively bigger. Because again, it's 3 meters longer, it's proportionally wider, it's proportionally deeper, it's then probably a bit proportionally heavier as well, because you've got the extra weight you need to carry to end up with even thicker bones. So yeah, it is a just colossal animal.
So Klaus, it sort of says that sort of 15, 16 tons.
So yeah, our numbers hit almost exactly 15 tons. I think we just rounded it to 15 tons at that point, because there's no point adding the 136 kilos on or whatever the hell the number was on an animal like this. So yeah, and that is our basically hypothetical largest ever, as in across the population, across a couple of million years. Again, based on we're using a bunch of estimates. We've got a bunch of gaps and things in here. This is not the answer. We're in no way, shape, or form saying like this is like the answer. This is our hypothesis. This is our best available interpretation from the data we have.
And we think that dinosaurs are like, things like crocodiles, which don't seem to have an upper limit to their size. It's just how old they get.
To a degree. So that one kind of goes backwards and forwards. I suspect the truth is that there are determinate growth dinosaurs that stop and indeterminate dinosaurs that carry on, and some that probably look like the former but are the latter because the growth is so minute that it's going to slow down and you're not really going to see it again. But this is just a pattern of biology. It's in terms of like there being really big outliers. This isn't anything to do with dinosaurs or reptiles. This is to do with biology. You see this all the time. If you look at the records of animals and how big they are of almost any species you come across, but particularly obviously big things where people have tended to measure a lot of them. The really biggest one that's ever been found is usually something of an outlier itself already, but also it is much bigger than like a normal, inverted commas, average animal. So, you will regularly see things like, a bull African elephant is 5 tons or 5 to 6 tons. It's in that realm. And the record is something like 10. It's double. It's massively, massively bigger than what you would normally see almost anywhere. And that alone is then the record, at least that we have found. We have not been accurately measuring the largest East African elephants for the last 2 million years while they've been knocking around in East Africa. So that's only the largest one that we have directly observed that we're happy about the number. So yeah, these things just go on and on. I fudged the numbers because I can't remember. When we started digging into this, I really wanted to have a section on whale sharks, which I think Jordan eventually cut out. I know it's definitely not in the paper, but because it's something I'm interested in a little bit, and one of my former students sent me some data on this. So until something like 1998-ish, the record whale shark was a smidge over 10 meters. So that's the biggest one we'd found, biggest fish in the sea. And then it went to 12, and then it went to 13, and then it went to 18 in about 15 years. It nearly doubled in size. And again, these are
in length.
Yeah. Yes. And again, these are, okay, they're fish, they're in the sea, you think they're hard to spot. But whale sharks, extremely popular for ecotourism, lots of research being done on them, very often swim in shallow waters in the same few places. And yet within a couple of decades, we basically doubled their maximum size. And that is length. So in mass, 6-fold increase. This happens regularly with things we haven't sampled very well. And at best, we've got 30, 40 T.Rex you can measure.
Yeah, which isn't hardly any. And also, we don't know really how much extra weight's on them in terms of how much fat they store.
Yeah, so, getting exact mass estimates is going to get harder and harder and harder because at really extreme sizes, maybe they get hyperneumatic and lose a bit of mass proportionally, but maybe they get really heavy, and so then they need disproportionately heavy, dense bones. This was part of the Spinosaurus stuff we talked about recently. Just bigger animals have denser bones, so they're going to weigh more than you expect. It's not just a linear extrapolation. But again, we're not too fussed about that. Again, I'm not saying like, oh, my, our 15-ton number is wrong. I'm just saying you need to be aware of all the caveats that go into this and stuff that basically we can't realistically assess and may or may not push it in various different directions. But the take home is, there's no reason. I just wanted to
jump in and explain what pneumatic is for people who might not know. Because pneumatic basically is the idea that the fossils the dinosaur bones have got lots more air pockets in them than, say, a mammal bone. So Alex's comment below that, a predator twice the size of a big bull African elephant is insane. It's going to be larger. It's going to look larger than that because it is pneumatic. So per cubic square of dinosaur, it's going to be a lot lighter than per cubic square of mammal. Maybe.
So for theropods and sauropods, yes, though Tyrannosaurs are not particularly pneumatic. And then again, if they have to get denser to hold up their weight, that's probably going to eat back into those numbers. But certainly for a lot of things, particularly the sauropods, so the long neck, long tail, Diplodocus, Apatosaurus, etc. animals, they are very pneumatic. And pterosaurs are flying reptiles. We see that they're annoyingly pneumatic, and indeed pneumaticity definitely increases with size on them. It's probably worth noting, since you put it back up, so Mark has not just scaled that animal. The hypothetical Rex in the background is not just the one in the front increased by 20%. he has scaled it according to certain patterns that are in the literature. Phil Curry did a paper years ago where he looked at this and tried to scale between kind of mid-sized, late juveniles, young adults, and big adults. And you see things like the head is actually getting bigger, the hips are getting bigger, and things like this. So Mark has scaled that stuff in. So yeah, that animal at the back is not just a scaled up clone. There are various proportions of bit which have been enlarged or shrunken according to Phil's maths to try and make it a bit more accurate.
So does that mean, so its eyes are probably relatively the same size then?
Yeah, I doubt, well, or even absolutely the same size. I doubt their eyes would increase very much in size at all. Because yeah, we've talked about this definitely, but you know, orbit size is basically directly correlated to eyeball size. And there's a reason that babies are born with giant eyes that effectively shrink as they get older, because yeah, you know, eye size determines how good your vision is and how well you can see in low light conditions. And I doubt a 30% or 20% bigger T.Rex needs 20% bigger eyes. It probably doesn't need any bigger eyes than the one below. And of course, you can probably grow that. You know, if they were really important, we'd see bigger eyes in younger Rexes. So the eye has probably stopped growing, the eyeball at least. Maybe the socket is getting a little bit bigger as the skull changes to keep the weight down. But I doubt they had much bigger eyeballs.
Okay. So what does this mean then? Does it mean that all of these paleo artists are just going to have to go and zoom, make their T-Rex just a little bit bigger?
Well, no, but as I say, that we were genuinely trying to kind of undermine a bit, really, this whole whose is biggest. You know, we've talked about this before, the fact that we even argue about whether or not I try not to, whether or not, you know, species A is bigger than species B, when both of them are hilariously incomplete. And, you know, already scaling, how long is the tail? Don't really know. How heavy are they? Don't really know. Are we using this metric or that metric? Are we factoring in this bit or not? You can get not almost any animal, but you can have things which are very comparable in size. And depending on quite how you scale it, you can make one bigger or smaller or bigger or smaller. But as I say, you know, we mentioned it earlier, the point really is that kind of pales into insignificance next to the bigger problem, which is the sample size. You know, you and I are about the same height, and if we had fragmentary skeletons, people could argue forever and a day as to which of us was marginally taller, which of us was marginally heavier. But we're both barely over 6 foot. And, you know, it wouldn't be too hard for me to find someone who's 6'4", let alone 6'8", let alone 7'2". So arguing about us doesn't really get you anywhere. What's interesting is the potential for what that means in terms of the ecology of these animals and the distribution of the body sizes within populations, and just like upper extremes. You know, biomechanically, a 15-ton Rex might not work, as in it might be so heavy and inefficient because it's so heavy that it requires so much effort to move around, and it's so effectively slow that it can't do very much and therefore can't hunt very effectively or whatever. But I think at least we've now got a decent hypothesis as a starting point for looking at that, because otherwise you're just left with the, you know, an unknown upper limit. Well, just how big could they get? Well, who knows? Well, now at least we've got more than a guess, but again, at least we've got a limit. Okay, 15 tons we think is a pretty reasonable estimate based on the available data. So let's go and test it. How would it move? How fast could it move? What would be its physiological efficiency at that kind of scale? Or would it be massively more resistant to cold and therefore could operate at a higher latitude or whatever? And so, yeah, it's a starting point, but it also means like the next time that someone goes, X has been found and it's the largest ever, you know.
It's the largest ever fossil. That's still cool, but it's probably not the largest ever dinosaur that existed.
But that's the thing, you know, Giganotosaurus and Spinosaurus, they're a good example in this case because they're such limited, you know. We've got the upper limit of Spinosaurus is basically estimated on a big snout, the one that's in Italy. And maybe really big Spinosaurs have really big heads, and he's not that big. Maybe really big Spinosaurs have proportionally small heads, and it's absolutely colossal. Maybe that is one of the 10 biggest Spinosaurus which ever lived, in which case that virtually is the upper limit of them. And then Giganotosaurus is exactly the same. If this is the smallest large Spinosaurus ever and the biggest large Giganotosaurus ever, then they're massively far apart. But we don't know, so arguing about it is really pretty meaningless.
Do we have time for a very good nerdy question by Alex?
Yeah.
Alex has, in the past, Dave has talked about the variability of the length of the tail in dinosaurs. Was there any variability in T.Rex, and how did they account for this in the paper?
So answer the first part, we don't know, because to this day, I think Sue has got the most complete tail, and that's not that complete. AMNH 3527, the other one, which is pretty good, has still only probably got half a tail or so. So we don't know if it varied based on what I've seen with everything else with the papers I've published. Yes, it did. Did we account for it in the paper? No, because really mass is much more important than weight. Mass is much more important than length and these linear dimensions. That being one of the reasons. Adding an extra 2 meters of tail will add some kilos, but in a 10+ ton washout, no one cares. So that kind of thing isn't really very important in this context. And again, that's another factor for trying to scale these things when people are arguing about who is longest versus who is heaviest.
I think the point is it's still going to be very scary if you got your time machine,
right? And
maybe avoid Montana in the late Cretaceous.
And these things are inherently interesting. T-Rexes and these other animals are already absurd outliers for what we see for most other terrestrial ecosystems for basically the history of life. It doesn't matter if Spinosaurus is 12 or 14 or 16 or 18 meters long and 4 tons or 6 tons or 8 tons. It's absolutely massive. It is far bigger than any other Spinosaurine and one of the biggest theropods. It just is. That's the interesting thing. So let's delve more into how it got that big, why it's that big, how it functions at that kind of size, why the others aren't functioning at that size, and worry far less about whether or not it may or may not have been literally, I've seen in some arguments, 20 centimeters longer than Giganotosaurus, depending on how you scale the stuff we don't have and don't know about, because that isn't interesting at all.
Oh, I don't know. I think there's something quite fun about.
All right, it was probably fun the first 17 times. Now we're up to the 17 millionth time. It's starting to pale.
People have to set pub quizzes and make sure they're accurate, Dave. That's all I'm saying. Anyway, thank you very much for your paper explanation, Dr. Dave Hone from Queen Mary University. I've been Izzy Lawrence, who's just sat here after a shower with floppy hair, looking like Anderson Cooper. Hi. But thank you so much for joining us. I see there's been quite a few people sort of popping in and having a lunch break. Sorry there wasn't much notice in this, but Dave literally found out about this like a few hours ago.
It was about 8:30. I got the email, so for a 12 o'clock.
And then we had about 3 hours message. And exactly, it wasn't very long. So if you want to find out more about the paper, you can find out about it. I put a link I put the name of it so you can find it. Also, we will be releasing a new episode next Wednesday, last Wednesday of the month. You get your fresh dinosaur stuff. And it's really nice to sort of see you guys. We should do this more often, we know, but we're very busy, important people, and it's very hard to do. So anyway, thanks very much, everybody. Should we roar at the end, Dave? 1, 2, 3. Oh, she says, trying to wait for.
Yeah, I was going to say.
No. It's literally my mouse just went, and I couldn't end it. This is so cool. We're so good at goodbyes, guys. We just don't want to leave. So anyway, see you soon.
Bye.